So here is a sample pulley question. I should have been slightly more descriptive, but you are to find the common acceleration of the particles, and you're also to find the tension in the string. So the best way to go about a problem like this is to try imagine what would actually happen. So as a little bit of a starter hint, the 20 kilogram mass will go downwards with its weight of 20g. The 10 kilogram mass will go upwards, and the tension will be acting like this. So these arrows are actually part of our free body diagrams that I've been talking about. So it's just drawing all the forces onto this diagram. And then you just have to do some resolving forces type of thing. So with that hint, give this problem a try, and when you're ready, come back for the solution. So here's the solution. The first particle I've labeled as particle 1. So it's 20g going in the direction of acceleration, and the tension is trying to stop it from accelerating. So that's 20g minus t is equal to 20, because that's the mass, times by the acceleration that we don't know yet. The second particle, particle 2, the tension is helping it accelerate. The 10g is trying to slow it down, and that's equal to the mass 10 times the acceleration. So adding these equations together, we get 10g, so that's 20 minus 10, is 30a. So dividing by 30, we get a is g over 3. As a fraction, that's about 3.3-ish meters per second squared. So 3.266666666 recurring. But to one decimal place, or two significant figures, it's 3.3 meters per second squared. Now, subbing that into, say, equation 2, which says that the tension is 10a plus 10g. So essentially adding 10g to both sides here. So we get 10 times g over 3, so that's 10g over 3, so 10 times 9.8 over 3, plus another 10 times 9.8. So the tension is 40g over 3, which, yep, is 131 newtons. If we're taking it as that accuracy. If we're not, then it's 130, so it depends on the accuracy that we're taking it to. But it is 130.6 recurring newtons, so I'll write that as 131 newtons. So the acceleration of the particles is 3.3 meters per second squared, with a tension of 131 newtons in the strings. Or in the string, rather.